When transformers were introduced in the paper Attention is All You Need, they changed how language models understand structure. Instead of processing sentences piece by piece, a transformer looks at the entire sequence at once, building connections between every part of it. It decides what matters, what relates, and what should influence the next prediction. Attention is the mechanism that makes this global understanding possible, and to see how it really works, we need to start at the very beginning. How the model first sees your sentence before any meaning can form. To understand this sentence, the machine first breaks it into small chunks. You can see these chunks as words, but the machine understands them as tokens. Later you will see that these tokens each have their own token ID. After this tokenization, the tokens get converted into high-dimensional vectors, which are called embeddings. These embedding vectors can be visualized in this vector space as different words aligning to different directions of this embedding space, simply capturing different meanings in each one of these directions. Also, you can think that different directions in this embedding space have their own neighboring positions. Words or ideas with similar meanings end up close to each other, while different meanings spread out in different directions. This is how the model keeps related concepts near and separates the unrelated ones. As we know, this word in this sentence has a meaning that is encoded as this embedding factor. But if we consider another sentence that also contains the same word, you will see that the embedding assigned to this word stays the same. That's the problem. The architecture isn't aware of the contextual meaning of the word. It just gives the same factor to the word, independent of the sentence it appears in. In other words, the meaning doesn't shift with context yet, even though we clearly understand it differently in each sentence. And that's our goal, to make these embeddings contextually aware, using the attention mechanism, so their meaning can shift based on the words around them. So to make this simpler, let's take an example. The hungry cat and mouse waited for food. We already know that each word first gets associated with some high-dimensional factors, which becomes its initial embedding. But these embeddings still don't know anything about their position in the sentence. So we add positional encoding, giving the model a sense of order. Which word comes first, which comes next, and how far apart they are. Now each word has an embedding that carries meaning, plus a sense of position. To move deeper into the attention mechanism, we need to reveal a certain trait for each word. For this, imagine the word cat being nudged by a special weight matrix called the query matrix. When we multiply cat's embedding with this matrix, we get a new factor, the query factor. This matrix is made of learned weights discovered during training through countless adjustments until the model figures out what matters. You can think of the query vector as the question the word wants to ask. For example, the word cat might be asking, "Does anyone here related food?" And the food might naturally say, "Yes, that's me." The query vector takes the original embedding and transforms it into a smaller space that represents the kind of question that word asks. But we want every word to ask its own question and look for relevance in the others. That's why we apply the same query weight matrix to every word in the sentence, giving each one its own query vector. And to get a response to that query, we now bring in the key vector. The key vector is what seems to answer the query. We generate the keys in the exact same way we get the queries, just using a different weight matrix called the key matrix. This matrix is also made of learned weights, discovered through many rounds of training and adjustments. The actual process of how these weights are learned is complicated and not important for understanding the attention mechanism here. You can think of the key matrix as transforming each embedding into a smaller space that represents the kind of answer that word can give. So now we have the queries that ask questions and keys that hold the answers. Once we have both of these, we need a way to measure how much one word should pay attention to another. In other words, we want to know the relevance score between every pair of words when they encounter each other. To do that, we take the dot product of each query with each key. These dot products fill up the grid of attention scores, showing for every word how strongly it should focus on the other words around it. Now, to visualize this more clearly, instead of showing the grid filled with raw numbers, it's much nicer to represent them with high opacity and low opacity cells. The brighter cells show higher attention scores and the dimmer ones show lower scores. In our example, the word hungry might give a high attention score with cat and also with mouse, so those cells would appear bright. But words like the or and might have much lower relevance, so their cells fade out with lower opacity. Everything you see here depends entirely on the dot products between the queries and keys, but there is a small issue. These raw dot products can become too large when the embedding dimension grows, and that makes the attention unstable. To fix this, we take these dot products and divide them by the square root of dimension of key query space. Even applying this scaling to just a single score already shows how it pulls extreme values back into a reasonable range. Once that score is scaled, we apply the same idea across the full set of attention scores. After the scaling, the values in these grids becomes much more balanced and easier to work with. Still, they're not in a form that immediately intuitive. To turn them into something that behaves like a clear, comparable set of weights, we apply a function called softmax, which you can also see in the Attention is All You Need paper. Applying softmax gives these grids numbers between 0 and 1, which makes them feels like a probability distribution. And if you look at each column, the values now add up to 1, and the same idea applies to all the other columns too. With this, you can point to a cell and say something like, this word gives 86% relevance to that word, or this one gives 94% relevance to another one, and so on. After applying softmax, we get this more refined and stable attention scores. Everything we've been describing so far, all these scenes and transformations, they all happen inside just one head of attention. But in the attention mechanism, to build a richer and more precise representation of contextual meaning, we don't rely on only one head. Instead, we use something called multi-headed attention, where the same process of single head runs several times in parallel. Each head learns to focus on different kinds of relationships, and together they give us a more stronger sense of context. We will come to multi-headed attention after we fully understand the single head of attention. Being focused on the single head of attention, we can see how the attention works for this sentence as one specific context. But of course, there are many other contexts where the same words may behave differently. In each new context, the meaning shifts, but the process we apply to them stays exactly the same. First, we activate the query and key factors by multiplying the query and key matrices with the embeddings of the words in the new sentence. This again gives us a set of query factors and key factors. Then we calculate the attention scores to know how much one word pays attention to another. In some contexts, certain words show high relevance, and in other contexts, the same words might show low relevance, all depending on the relationships inside that particular sentence. After that, we scale these raw scores by dividing them with the root over of dimension of query key factor, and this scaling applies across all the grids we form. Then we apply softmax to these grids, to both of these examples and to any other context as well. And that gives us a clean attention pattern for each sentence. In the end, we get a full attention grid for any context we consider, just like the one we built for our main example. The hungry cat and mouse waited for food. After understanding how the attention mechanism works across different contexts, let's return to our central example. The hungry cat and mouse waited for food. So far, we have built the attention pattern for this sentence. But now, I want you to remember the overall goal of our model. It needs to predict the next word efficiently. And to do that, this full sentence is broken into slices, where each slice represents a part of the sentence in the sequence. The attention mechanism allows each word at each step to perform many operations and connections so that it can predict the next word. This all happens in parallel, which makes training much faster and more efficient. But here a problem appears. In this scenario, the later words in the sentence can give attention scores to the earlier words. That's not what we want, because it gives those earlier words unnecessary influence that they shouldn't have. It's almost like the model is cheating by looking at the future while trying to predict the next word. So we want to prevent these later words from contributing relevance to the earlier words at all. One idea would be to simply set those future leaking spots in the grid to 0. But if we do that, the columns wouldn't be normalized anymore. They wouldn't add up to 1, and that breaks the idea of having a proper distribution. So we need a method that blocks the future information while still keeping the attention numbers meaningful. The solution is elegant. Instead of turning those future positions into 0, we turn them into negative infinity. Then when we apply softmax, those positions collapse to exactly 0, and the remaining ones still form a valid probability distribution that sums to 1. This prevents the future from influencing the past, while keeping the math consistent. This entire process is called masking. Now, the attention pattern finally has the right meaning, cleanly prepared for the next computations. At this point, you may remember that we already have two matrices, the query matrix and the key matrix, both sets of learned weights. Let's introduce the third one, the value matrix. This value matrix also comes from the set of learned weights, lives in the same dimensional space as the query and key matrices. Now, look back at the attention pattern. We already know how each word gives relevance to the others. And now comes the part where information actually gets shared from one word to another. Take this pair of words and the attention score between them. We want the first word to share its information with the second word, nudging and refining the meaning of that second word. To do this, we transform the first word's embedding using the value matrix. Multiplying the embedding with the value matrix turns it into a more polished version, a version that carries exactly the kind of information that needs to be shared forward. This transformed vector is what we call the value vector. It contains the meaning that will travel across the sentence. Next, this value vector gets scaled by the attention score. You can think of the value vector as the information and the attention score as deciding how much of this information should be shared. If the attention score is 52%, then 52% of value vector's meaning flows from the first word into the second. After this multiplication, we add the resulting vector to the second word's embedding. So the meaning of the second word shifts according to the information it receives from the first one. Now, let's take the value vectors inside the full attention pattern. And then, after that, we scale each value vector with its attention score. And then we add up all the resulting values in that column. This gives us the weighted sum for the column, a new embedding, that represents how much and which information the word collected from all the other words. This weighted sum is what makes the embedding of this word more contextual, more aware of its surroundings. We repeat this weighted sum process for every column in the grid, giving us a set of full, refined embeddings for all the words in the sentence. And to make these embeddings even more meaningfully contextual, we add these refined embeddings back to the original embeddings. This new connection helps preserve the original meaning while blending in the newly gathered contextual meaning, a very important idea for the later steps in the model. And remember, everything we've described so far, the queries, keys, values, attention scores, weighted sums, all of this happens inside just one head of attention. In multi-headed attention, the same process runs across multiple parallel heads, each focusing on different aspects of meaning, giving us an even richer and more refined representation of the sentence. But before moving on to the multi-headed attention, let's take one more case to deepen our understanding of the single head of attention. So far, we've only seen how a single head works on short sentences through small, simple context. But attention is far more powerful than that. It can work on much bigger context too, like an entire article. And when it processes something large, the attention mechanism starts forming pattern, not just between nearby words, but also across long distances. Short-range connections and long-range connections both influence the result. This ability to catch different types of relationships, close ones and far ones, is what allows the model to read the whole article and generate a meaningful summary. And if you make even a small change in the article, the attention mechanism recalculates everything again, forming new patterns and new connections, which in turn changes the summary. This is one of the beautiful things about attention. It can detect and combine patterns in so many different dimensions that the number of ways it can understand becomes almost uncountable. Now, coming back to the article example, if we visualize its attention pattern as a grid, you will see something much larger than the grid we had for our central sentence. That's because the size of the attention pattern grows with the square of the context size. In simple terms, if your context becomes twice as long, the attention grid becomes 4 times bigger. If your context becomes 10 times longer, the grid becomes 100 times bigger. So as the context size increases, the attention pattern explodes in size as well. This gives us a sense of how powerful and also how demanding the attention mechanism can be, even in a single head. And now, moving into the multi-headed attention, everything we've done so far inside a single head begins to run in parallel across many heads, each extracting a different aspect of meaning. Coming back to our central example, the hungry cat and mouse waited for food. We've only seen one attention head in action, but in reality, several other heads are working at the same time. Take the word cat. In the first head, we already refined its meaning by multiplying the value vectors with the attention scores, and then taking the weighted sum. But that same process also happens in every other head. Each head produces its own weighted sum results for the word cat, each one capturing a different nuance. Maybe one head notices nearby relationships, another notices long-distance connections, another catches thematic similarity, and so on. Once all these heads finish their work, we concatenate the weighted sum output for the word cat. This gives us a large combined vector that holds all the different perspectives learned by each head. But here is the important part. We cannot directly add this concatenated result to the original embedding. If we did, the dimension wouldn't match, and more importantly, the heads wouldn't meaningfully interact with each other. Before adding anything back, we need all these heads to mix their information, to talk to each other. To do that, we use another learned weight matrix called the projection matrix. We multiply this projection matrix with the concatenate vector. This projects all the different head-specific pieces of information into a single unified space, where each head's contribution becomes aware of each other. In other words, after this projection step, the insights learned by head 1, head 2, head 4, or maybe even some long-range head like head 12 or head 26 all blend together. The projection step allows all these parallel attention heads to share their discoveries instead of staying isolated. Only after this projection do we add the refined result back to the original embedding of the word cat. This addition blends the previous meaning of the word with the newly gathered contextual meaning. And of course, this exact process happens for all the other words in the sentence, all in parallel, giving every word a richer, deeper, and more contextually aware embedding. After seeing how multi-headed attention runs in parallel and blends all its insight together, you might think we are finally done, that now we have the full contextual meaning of every word in our sentence. But that's not actually true. What we just explored is only the refinement happening inside a single layer of the model. Even though multi-headed attention extracts several different perspectives at once, it still represents just one stage of understanding. Transformers don't stop there. They stack many of these layers on top of each other, one after another, and each layer tries to uncover a deeper, more abstract meaning than the previous one. And in between these attention blocks, there is something else at work, a component called the multi-layer perceptron. You can think of the MLP as a small neural network sitting between layers, reshaping and transforming the representations even further. It pushes the embeddings into new directions, emphasizes certain features, and helps the model detect patterns that attention alone might miss. We do not need to dive into the full details of the MLP yet. Just remember that every layer has both a multi-headed attention module and an MLP that further processes the output. Together, they form a sequence of transformations. Layer after layer, the model keeps refining the meaning of the words. The attention blocks keep discovering relationships, and the MLP blocks reshape those discoveries into richer, more useful representations. And importantly, what happens in each new layer is the same kind of process we've already seen. Attention again, queries again, keys again, values again, but now applied to the outputs of the previous layer. Each layer looks at the sentence with a slightly different mindset, extracting more nuanced structure every time. So even though one layer's multi-headed attention already gives us a deep sense of context, the model strengthens and sharpens that understanding again and again across many layers. Only after moving through all of them do we reach the truly powerful, fully contextual embeddings that transformers are known for. I want you to remember again, the ultimate goal of our model is to predict the next word. Everything we've been exploring, the single head of attention, the multi-headed attention, and even the layers with their multi-layer perceptrons, all of it exists to support this one goal. Now it's time to get an intuitive sense of how next word prediction might actually happen. The exact mechanism inside the model is extremely complex and honestly too deep to fully break. But we can build a meaningful analogy that captures the essence of what's going on. Let's come back to our central example, the hungry cat and mouse waited for food. By now, you can imagine that the embeddings for this sentence have gone through many attention heads and many layers, each layer applying multi-headed attention, then passing through an MLP, then another layer and another. After moving through all of these stacked layers, the embeddings become the final richly contextualized version of the entire sentence. Now comes the question, how can these embeddings help predict the next word? One way to think about it is this. The embedding of the second word doesn't only represent the second word anymore. It now holds pieces of meaning gathered from the first word as well. Similarly, by the time we reach the third word, its embedding carries the meaning of the first, second, and third, all merged into a single representation. And this keeps going, step by step. In our sentence, the final word food ends up carrying the compressed representation of the entire sequence. It becomes a single vector that captures everything the previous words expressed, blended together with its own meaning, almost like a summary of the whole sentence, living inside one final embedding. To predict the next word, the model takes this final embedding, this condensed representation of the full context, and mixes it with everything the model already knows from training. Its vocabulary, its learned grammar, its world knowledge, its statistics of how sentences usually flow. Using all of these, it produces a probability distribution and selects the most likely next word. Once that next word appears, the process repeats. The newly predicted word now becomes part of the context, so the recent two words share information again, merging their meanings. This prepares the model to predict the following word, and after that, the next one, and again and again. Step by step, the model keeps compressing the meaning of everything it has generated so far into the most recent word's embedding. That embedding becomes the representative of the entire story up to that point. That's how the ongoing generation continues until we end up with a complete sentence, a paragraph, or even an entire narrative. And this at a high level, how the chatbots and modern AI models generate text smoothly, continuously, and beautifully. The underlying system is built on a complex chain of mathematics, optimizations, and deep training dynamics that goes far beyond what we covered. But everything that looks magical on the surface is built from the fundamentals and first principles we explored together. Embeddings, queries, keys, values, attention, multi-headed attention, and layers stacked on layers. That foundation is what makes the entire generation process possible. But there is one more thing you need to remember. During training, when the model is predicting the next word at each step, it doesn't magically get everything right. Especially early in training, the model predicts the wrong word or gives a low quality result, even after tons of operations happening underneath. And instead of complaining about these mistakes, we actually use them. How? By calculating something called loss, using a cost function. The loss tells us how far off the model's prediction was from the correct next word. Then, using this loss, the model updates its weights so that the next time it predicts, it gets a little bit better. This cycle repeats millions or even billions of times. Every prediction, every tiny error, every correction contributes to strengthening the model's ability to predict more accurately. This is why training is so compute heavy. The model learns next word prediction not by getting things right instantly, but by making an uncountable number of mistakes and improving from each one. The attention mechanism plays a huge role here, helping the model find connections, refine meaning, and reduce the loss over time. Everything we've explored so far belongs to one specific form of attention called masked self-attention. There is another important variant called cross-attention. Unlike self-attention, cross-attention connects to different streams of information. The queries come from one source, while the keys and values come from another. Instead of a sequence attending to itself, one representation attends to an external one. A classic example is machine translation. The source sentence produces the keys and the values, and the target language produces the queries. The same mechanism appears in many other settings: audio transcription, text-to-image models, image-to-text systems, and more. So far, we've explored the attention mechanism as a sequence of simple ideas working together, from embeddings to attention to layers and context. Everything we saw takes the same principle: refined again and again. For now, this foundation is enough. In the next video, we'll build on it and look deeper into the systems that make modern artificial intelligence and machine learning work.